Hello, everybody, and welcome to what I think is going to be one of the best presentations of the year. It is my distinct pleasure and privilege to spend time with my good friend and mentor, Chubb Michaud. Chubb started in the water treatment industry a very long time ago. He's the CEO and technical director of Systematics Company since 1982. If it's cold or warm and wet, he's been there. He's forgotten more about ion exchange than most people will ever learn. Graduate of the University of Maine with bachelor's and master's degrees in chemical engineering, 18 years with Roman Haas, two-time recipient of the PWQA Robert Gans Award, the WQA Award of Merit, the PWQA Hall of Fame, and the WQA Hall of Fame, and also the author of more of 100 papers that have been published and spoken probably in every civilized country around the world about the magic world of water. Chubb, teach everybody about ion exchange options for nitrate reduction systems.
Greg, thank you very much for that introduction. Absolute pleasure to be here. I'm going to be talking about the ion exchange options for nitrate reduction. At this trade show, well, sort of. The presence of nitrates and nitrites in our food and water is associated with an increased risk of gastrointestinal cancers in adults and methemoglobinemia in infants. While our dietary guidelines encourage the consumption of leafy greens and other vegetables, the majority of our nitrate intake actually comes from foods and only about 20% from beverage, including drinking water. Ingested nitrates support the production of nitric oxide in the body. That's a good thing. Nitric oxide then gets oxidized to nitrites, a not so good thing. Also, nitrate can be reduced to nitrite by the biopopulation in the GI tract. Now, with 80% of our nitrate being introduced by food and only 20% in the beverage, why the fuss? Well, the thing is, everybody consumes nitrates. Some people have no nitrate in their water, other people have a bunch. It's an 80-20 ratio in terms of consumption, but not on an individual basis. So foods high in nitrates, it's all the stuff your mother told you to eat: leafy greens, beets, celery, citrus, nuts, and my two favorites, dark chocolate and red wine. My focus today will be on the selection of an ion exchange resin for the removal or reduction of nitrates and nitrites in potable water. Along the way, I will discuss the chemistry of nitrates, sources of nitrate in groundwater, health effects of nitrates in the diet, safe limits for nitrates in water, methods of nitrate and nitrite removal, an introduction to ion exchange chemistry, and then the use of ion exchange for nitrate-nitrite remediation, and that will be the main focus. Then I'll discuss the selectivity of ion exchange resins and how that plays on nitrate reduction, give some examples of exchange ratings and design ranges for ion exchange. I will also, along the way, give my recommendations, and we'll have some conclusions and any questions if we can fit them in. What I like for the audience to take away is understanding the source of nitrates, the dangers of ingested nitrate, what is safe, the market potential for remediation, and how to fix high nitrates. Then what is your responsibility as a provider of this equipment? If we look at nitrate, it's made up of nitrogen and oxygen. Here's the two side by side on the periodic table. They appear in a bright red, which means they're gaseous. Now these two can coexist side by side. 99% of our atmosphere is actually an 80-20 blend of nitrogen and oxygen. Fortunately, they don't react together spontaneously. The nitrate ion looks like this. It's NO3. And if we look at the periodic table, we see that nitrate can have a +5 valence, oxygen -2. So the green ball represents the nitrogen, The three red balls around it represent oxygen. And there's a line that goes down the periodic table. You may not have ever noticed, but it's there. And everything to the right of that line forms compounds with oxygen, such as borate, carbonate, nitrate, silicate, phosphate, sulfate. If it ends in 8, it's an anion. So we have a +5 with a -6, total -1. Anions are negatively charged. This is an anion. Nitrite, we pick up the alternative valence for nitrogen, which is 3, and we have 2 oxygens. Again, +3 -4 is equal to a -1. It is also an anion. Now, nitrate and nitrite in water has no taste, no odor, no color. It's not obvious. You have to test. Where does the nitrate come from? Well, it's an inorganic, and although it may be naturally occurring, the primary sources are man-made. Fertilizer runoff, nitrates are used in fertilizer, livestock waste, improper disposal of sewage, septic systems. Nitrates are very, very soluble, and they can penetrate deeply into groundwater. So even though they're laid on the surface, a little irrigation or a heavy rain, and they sink well down into the aquifer, end up in the private wells. Water is not the only source. As I mentioned earlier, nitrates are also contained in vegetables such as beet, celery, lettuce, and spinach. Overall, most nitrate comes from food, but again, it's not evenly divided by way of food. If we look at the exposure, the most significant effect of exposure of nitrates in water is methemoglobinemia, particularly a problem for infants under 6 months, otherwise known as blue baby syndrome. And it carries a fairly high mortality rate of about 9%. Now, after about 6 months of age, the bacteria in the GI tract of infants changes to a little more mature, and the system does not convert nitrates to nitrites as readily. So they grow out of it, but it's a real danger in the first 4 to 6 months. Now, when ingested, nitrates convert to nitrites in the digestive tract and then get absorbed into the bloodstream. Nitrites react with hemoglobin to form methemoglobin, which is a much less efficient molecule for oxygen transport. The result is oxygen deprivation and suffocation, and this can be fatal for infants, the elderly, and or the immunocompromised individuals as well. Short-term exposure to high levels of nitrates in adults can cause nausea, vomiting, breathing problems, eventually muscle paralysis. Long-term exposure is believed to be carcinogenic. Nitrates and nitrites are not particularly toxic per se. The LD50 for nitrate is around 1,500 milligrams per kilogram. For the average individual, that's about 3 or 4 ounces to be toxic. But keep in mind, LD50 means lethal dose 50%. So an LD49 is not safe. LD50 says if you consume this much nitrate, like 5 pounds of bacon in one sitting, you have a very good chance of becoming very ill. Now, nitrite, being that it's already converted to the reactive stage, is 10 times more toxic. The limit is 150 for the LD50, 150 milligrams per kilogram of body weight. So you're looking at less than a half an ounce. Nitrates can also react with amines and amides in the body to form nitroso compounds. These are known to cause cancer. According to the European Food Safety 2017 guideline, the acceptable amount of sodium nitrite is 0.06 milligrams per day per kilogram of adult body weight. For the average 70 kilogram person, about 170, 80 pounds, That's about 4.2 milligrams of sodium nitrite a day. Now, cured bacon contains about 120 parts per million of nitrite, which is about 4.5 milligrams per slice. Now, you're looking at a known level where you could be in trouble, and this is a single slice of bacon. So although an apple a day may keep the doctor away, that's good. One bacon-wrapped hot dog a day, that's not so good. Other studies on nitrate consumption, independent studies, both home and abroad, are indicating that nitrates consumed in drinking water above 0.14 parts per million can lead to an increased risk of colorectal cancer. Now, this is a claim that is flatly rejected by the US EPA, and they absolutely refuse to review the so-called safe limits of nitrate and nitrate in our drinking water. There's a reason for that. I'll get into it when I talk about the MCL. High nitrate consumption can lead to complications with pregnancy. Fetal development is impaired. Nitrates can block iodine uptake in the thyroid, leading to hypothyroidism. The US EPA has established an MCL, max contamination level, of 10 ppm of nitrate nitrogen and 1 ppm of nitrite nitrogen as of 1975. The MCLG, the ultimate goal, is the same. And please note that little asterisk, the MCL for nitrate levels does not apply to private domestic wells. So how did this limit come about? Well, back in the 40s, it was noted by a pediatrician in Iowa that healthy babies being sent home from the hospital were returning in just a matter of weeks, and they were blue. And they dubbed this blue baby syndrome, and they sought to find out what was the cause. Well, the investigation came down to it must be the water, because the diets were the same. They did note that mothers that were breastfeeding didn't seem to have the problem, so it led to the water. And when they tabulated the nitrate, the analysis of the water, the nitrate was the only thing that was really a variable. And in waters above 10 ppm of nitrate nitrogen, the majority of the illnesses were occurring in the high nitrate water, and there were no cases reported below 10 ppm. Thus, 10 became the limit. There was no research done. It was just a paper study. No one has ever suffered from a nitrate deficiency. Boiling or using water in cooking only concentrates the nitrates, so you can't get rid of it easily. Consuming water with nitrates above the MCL is unhealthy and can be dangerous for adults and infants. But consuming water with nitrates below the MCL may still be unhealthy. There are 9,000 utilities in the USA with nitrate levels between 5 and 10 ppm. US utilities with moderate nitrate levels are mapped out, and you'll notice that they seem to be concentrated in the farming areas, livestock areas, combination of fertilizer, combination of animal waste, and the rural communities having a lot of septic systems. A 2007 US Census report shows that there are actually 15 million households that are served by private wells, with 10% of those actually above the MCL. 10% of 15 million households above the MCL. Taking that up to 2020, that number has grown to about 20 million, with 20 million households and 10% above the level. With private wells, the MCL rules do not apply, but the consequences do. Not only is the presence of nitrates and nitrates a growing problem, it also presents a heck of an opportunity. I mean, you look at 2 million possible households currently living off feed streams above the MCL of 10 ppm. Now, if those systems were all put in place and they cost, say, $1,000 a piece, this is a $2 billion potential industry in the US alone. Now, take a wild guess at what the worldwide sales of water softening equipment are for residential. Worldwide, about $2 billion. So it's an equal market. It's worth going after, but it carries its responsibility. Now, what does the MCL mean? The US EPA established a max contamination level, which is the highest level of that contaminant that is allowed in drinking water. MCLs are set as close to the MCLGs as is feasible, using the best available treatment technology and taking cost into consideration. MCLs are the enforceable standards. Now, I emphasize the word cost because when you look at 9,000 utilities that are below 10 but over 5, and in my opinion in a danger zone, the cost of treating all of those wells is incredible. I mean, it puts a heck of a burden on the municipality. So safety may be and probably is compromised due to costs. But is the MCL of 10 ppm safe? The presence of nitrate and nitrate in our food and water poses a much greater risk than we care to admit. 10 ppm is not a safe limit. It's legal, but it's not safe. 5 ppm should probably be considered as a reasonable MCLG, a reasonable gold. That's my opinion. That's 9,000 utilities. That's 2 million private wells that would have to treat their water. You should promote nitrate and nitrite reduction on the basis that the MCL is not necessarily a safe level, even by the EPA definition. It is simply a legal level. It might just be the largest untapped market in the country, in excess of $2 billion. Now, the 10 parts per million nitrate nitrogen is often confusing. I get many calls saying, I've got 32 parts of nitrate in my water, is it safe? Well, if it's ion, not safe, but it's legal. If it's nitrate nitrogen, that's way over the limit. Now, nitrate has a molecular weight of 62. Nitrogen has a molecular weight of 14. So if the nitrogen is what's measured, then you have to convert that. So you would multiply the nitrate nitrogen level by 62 over 14 to convert it to nitrate ion. So the MCL of 10 times 62 over 14 is equal to 44.3 of nitrate ion, milligrams per liter. The ppm of nitrate ion times 50 over 62 converts the nitrate ion to parts per million as calcium carbonate. And this is what we use to work with for determining capacities. So that number is 35.7 of nitrate as calcium carbonate, about 2 grains per gallon. So 10 ppm nitrate nitrogen is equal to 44.3 of ion, 35.7 as calcium carbonate, and 2.1 grains per gallon. To remove nitrate, we can use reverse osmosis. This often is advisable if we happen to be accompanied by very high TDS or some other things in the water. It's reported to be 83 to 92% effective. I think some of the newer membranes may be higher than that, but it produces way too much wastewater to be practical for centralized municipal treatment. It's an excellent application for point of use filtration, treating only the drinking water. There's no evidence that nitrate penetrates the skin, so you're only concerned about ingestion. Ion exchange is also used typically as a single bed salt regenerated column, very similar to a softener, but with a different resin and a little different tender loving care and feeding. It can reduce nitrates to non-detect levels, which actually on a municipal basis allows for a higher level of blending. And by far, this is the most widely used technology for municipal applications for that reason. Why use ion exchange? Whoa. A proven process with a small footprint. At 10 gallons a minute per square foot, 1,000 GPM system is only 2 8-foot diameter tanks. It's very flexible in its flow rate. You can go up and down with it all the way from 4 to 15 gallons a minute per square foot. You can turn it off, turn it on 20 minutes later. There's no pumps to start up and worry about. There's no membranes to depressurize. So it's an on again, off again, ideal for residential application or commercial application where the water flow varies and it can be turned off and started at 2 o'clock in the morning. Relatively small waste volume compared to RO. It only takes about 80 gallons a cubic foot to regenerate ion exchange, which is only about 2 to 3% of its volume. It can reduce nitrates and nitrates well below the MCL, and which really lends itself to blending. Very high reliability factor. We've been using ion exchange for over 50 years, and it can remove other trace anionics, such as uranium, chrome, selenium, arsenic, and I put a little asterisk on that arsenic, and I will explain that in a bit. Why not? Well, it increases the chlorides in the product water, which can increase the corrosivity. Somebody presented me with a photograph of a set of stainless steel knives yesterday, and they were badly corroded. And I said, well, what's the system? Well, it was a nitrate system with a salt regenerated anion, followed by an arsenic reduction system. Very prudent. The only thing is, it was a 1900 part per million water, so they were doing the dishes in 1900 parts of chloride, and that is very corrosive. It does not destroy the nitrate, it only removes it, unlike bioremediation that can actually convert it back to nitrogen. It produces a high TDS waste. This is something you have to get rid of, 10 to 20,000 ppm. Capacity will vary with the feed water composition, so it's not a 100 gallon a minute system, it's a so many gallon system, run it at whatever flow you want. There are some TDS limits that you can operate at. I mentioned we saw a 1900 the other day. 2500 is considered a maximum TDS for a gel type resin, and I will explain that later. Standard strong base anion gel resins typically used are not nitrate selective. What does that mean? It means that they prefer sulfate and nitrate is secondary. The nitrate selective resins, however, which are nitrate selective, are deselective for sulfate. They're also deselective for arsenic. So that's another precaution that I will go into. Contaminants can concentrate in the spent brine. You may not know they're there, but when you regenerate the resin, you will have a several hundred or several thousand to one concentration that may exceed some set disposal limit. So you must have a decent water analysis so you know what's going on. Ion exchange 101. Ion exchangers are functionalized plastic beads that react like acids and bases and or salts in water, except they are themselves insoluble. That means that when they enter a reaction, the reaction product stays behind with the resin and it's separated from the water stream. An example of this is your everyday softener. Here we have feed water represented with calcium chloride, magnesium sulfate, and this yellow ball represents the ion exchange resin in the sodium form. Now, the calcium and magnesium, having a stronger charge and a heavier weight, are picked up preferentially by the resin, and it releases the sodium. So our calcium chloride becomes sodium chloride, magnesium sulfate becomes sodium sulfate. Well, we can do the same thing with an anion exchanger, except we're working on the other end of the salt molecule. With sodium regenerating a cation, the chloride regenerates an anion. So in this example, I've got sodium nitrate and magnesium sulfate passing through an ion exchange bed, and the nitrate and sulfate are picked up, and downstream is sodium chloride, magnesium chloride. Everything is converted to the chloride. Here's a photo of a gel resin. You've all seen these. If you look at them under a microscope, you can see right through them. They're called gel because they're transparent. This upper right-hand photo is a macroporous bead. And to look at it, it looks like a cue ball or a snowball. But if you blow them up, you get a chance to see what they really are. I mean, it looks like a giant ball of corn puffs or something. But what you see is a continuous solid phase where all of the plastic in the bead touches all of the plastic in the bead. So it's a very strong three-dimensional network. What you don't see is that these porous portions go all the way through the bead. So you have a continuous solid phase and you have a continuous porous phase. So water passes through the bead. It's not diffused through slowly as in a gel. It can pass right through the bead, exposing all of this surface area to the water. Now, the surface area of a typical macroporous bead is in the range of 1,000 square meters per gram. This is equivalent to activated carbon, extremely high surface area. Why do resins exchange? Well, there's two things. One is selectivity, and that determines what it picks up. And then there's equilibrium, which is determined by what is it competing with. Now, here's where selectivity and equilibrium go hand in hand. Ideally, in a nitrate removal system, we would like nitrate to be the highest selectivity, much higher than chloride, because the resin's in the chloride form, and when nitrate enters the resin bed, we want it to exchange for the chloride. We would like the chloride to be greater than the sulfate because we don't want to pick up the sulfate. And it's okay if that's equal to the bicarbonate because we aren't concerned about sulfate and bicarbonate. In regeneration, we want the chloride to be much, much, much stronger than the sulfate and the nitrate and the bicarbonate because we want it to strip everything back off. In reality, however, the gel resins prefer sulfate to nitrate over chloride and bicarbonate, so they got part of it right. And in regeneration, they sort of follow the rule. The chloride becomes preferred over the sulfate, but it's not as strong as is the driving force in a gel resin. Take a look at the ion exchange selectivity, and this will help explain the equilibrium and selectivity issue. Now we've blacked out the strong acid. We're going to concentrate on the strong base anion and the relative selectivity. The resin's in the chloride form, so we're going to assign a value of 1 to the chloride and say, okay, everything else relative to the chloride. Well, we see that nitrate is 3.2. That's a pretty good, it's 3 times more selective than chloride, so that exchange works very well. However, we also notice that nitrate is 9.1 to 1. It's 9 times more selective, and it's almost 3 times more selective than nitrate. So we're going to pick up sulfate first. Now, any reaction can occur in ion exchange. It's a matter of how clean the resin is. If it's an anion in the water and it's not present on the resin, it will pick it up. So the evidence for that is that we use anion resins as dealkalizers, where they have to pick up bicarbonate, and that the preference for chloride over bicarbonate is almost 4-to-1. It's 10-to-1 over hydroxide and 15-to-1 over fluoride, yet the reaction still occurs. But in the long run, it gives us this selectivity of sulfate over nitrate over chloride over bicarbonate. So sulfate, nitrate, chloride, bicarbonate. All anion exchangers will exchange for chlorides, will exchange nitrates for chlorides. So any strong base anion is going to work at reducing nitrate. But resins have different selectivities based on their chemistry and their capacity and the composition of the water. The proper selection will depend on the water analysis. The choice of filter design will impact the resin of choice. What does that mean? Well, if you have a twin alternating system that runs X number of gallons with no reserve and then regenerates, that's a different safety issue than a single tank that you might overrun. So they may take different resin choices based on the design. The degree of automation will impact the resin choice. If you're in a municipal plant and you're monitoring the gallons and you can stop at 12:15 in the afternoon, switch to another system, certainly automatically you are much safer than, again, a single tank that's run on a time clock or even on gallons. So how do these resins differ? Well, they differ functionally. They're all strong base, but they differ functionally by composition. The cross-linking level, the uniformity of the cross-link, the matrix type, gel or macro, all contribute to charge density and therefore contribute to selectivity. Now, I've drawn out a couple of different ion exchange models to show you how they differ. In the upper left, we have a vinyl benzene, where this is the vinyl. And so you don't get misled by the word vinyl. This is not like your artificial leather car seats in your 53 Chevy. This group is actually an ethylene. So it's a 2-carbon with a double bond in between. And it's shown here with one of the hydrogens substituted for a benzene. Any one of these hydrogens can be replaced with another chemical. So if we learned back in the 50s that we could polymerize ethylene by breaking this double bond and extending it out on either side. And that gave us polyethylene. It's a polymer of ethylene. If we substitute one of the hydrogens for a methyl group, a CH3, we have polypropylene. We put a chloride in there, we have polyvinyl chloride. Put 2 chlorides, we have vinylidene chloride, saran wrap. Substitute all 4 of them with fluoride, and you have polytetrafluoroethylene, there, PTFE, Teflon. Put in alcohol, polyvinyl alcohol. Put in acetate, polyvinyl acetate. So it's a very versatile group. This group is what's called vinyl. It's not vinyl chloride, it's vinyl. So we have a vinyl and we have a benzene, and that's called vinyl benzene. We call it styrene. Now, if you happen to have a vinyl group on either end of that styrene, it's called divinyl benzene. So we've all heard of styrene divinyl benzene. How does that work? Well, here's styrene. Here's polystyrene. Let's put another reactive group on the bottom of this styrene, and we'll pick up another chain, and that's called cross-linking. So we have all strong bases are quaternary amines. Now, what does that mean? Well, first, we can react this benzene group with we can chloromethylate that by adding this group to substitute for a hydrogen on the ring. And once we attach that group, we can react that with trimethylamine, which is an ammonia where the hydrogens have all been substituted with methyl groups, and we end up with something that looks like this. There's our original amine, and here's the trimethylamine with the nitrogen. So now we have 1, 2, 3, 4 methyl groups. That is what a quaternary amine is. The chloride remains, and you may recognize that that is the part of the resin that does the reaction. This is what we replace with nitrate. Now, we know that we can change the selectivity of the resin by adding a little interference to this chemical group. So this is a type 1 strong base anion. If we, and there's our chloromethylation. Now here's a dimethylethanolamine, and this is called a type 2, and you can see that it still has the original trimethyl, but there's an ethanol group here. So it lengthens the chain and changes selectivity. It also weakens the strong base and makes it easier to regenerate. When we go to a nitrate selective resin, we add to the chain. This is showing a triethylamine, but we can also do a tripropylamine, and we lengthen those chains and we change the selectivity. And we go to the ultimate tributylamine, where we've really added a lot of interference for something to get to that chloride. It has to be fairly small, not too bulky. And this is called a super selective resin. Now I call it the hummingbird effect because trimethylamine is a little bit like a bee on a flower, whereas the tributyl, you got to have a special proboscis to get down into that flower. So this is the hummingbird effect. Again, we look at selectivity. We see a 3-to-1 nitrate over chloride. We see a 9.1 to 1 for chloride, for bicarbonate, sulfate over chloride. We also have to look at the ratio of sulfate to nitrate because that's our competition. A gel resin is going to take both sulfate and nitrate, and there are reasons for that to be preferred. Nitrate Select is going to take both, but it's going to selectively drop the sulfate. So here's selectivity. Sodium nitrate, magnesium sulfate. We're picking up the anions, releasing chloride. That's our gel resin selectivity. And let's look at a tank in service and see what really is going on. So here's our sulfate nitrate chloride bicarbonate, typical water going into a bed of chloride resin. Now in the middle of the run, we've picked up the sulfate first, then the nitrate, and the bicarbonate now is actually starting to right at the fringe of breaking through. And the result is we're still putting out all chloride water. Now, approaching exhaustion, the sulfate is the majority of the resin, occupying the majority of the resin, followed by nitrate. The bicarbonate has broken through, and we're still, following it with chloride in the raw water and pushing out chloride bicarbonate combination. So if you monitor pH, this would be an indication. The pH would start to go up. This would be an indication that, hey, you're right on the fringe. Now, I have to send out a red flag here. The fact that all anions in solution carry a level of negative charge. Therefore, all anions will be exchanged onto an anion exchanger. There's a selectivity order based on the level of charge and the chemistry of the resin as to what gets picked up. There's also a de-selectivity order by which exchanger will give up some of those anions that are picked up in place of stronger charges. So the more preferred ion continues to be picked up at the sacrifice of the lesser selective. So you may pick up something that you don't even know is there, concentrate it on the resin, and then release it back into the treated water stream at much higher levels than the original. Let's take a look at this is referred to as dumping. And dumping has to be understood, and it has to be controlled and designed for. So let's take a look at the actual ionic level in a feed stream as a run progresses. Here's a line representing the influent feed. They're not all equal. I'm just using that to represent this is all the bicarbonate, this is all the chloride, and so on. Here is a breakthrough level of each individual, depending on whether we're operating for sulfate reduction or a dealkalizer. We have a breakthrough level. So here's the beginning, middle, and end of the run. What's going on? Well, here's our 3 feed streams. We're not counting chloride because the resin's in the chloride form. So here's what happens with bicarbonate. We pick it up in the beginning, mid-run. This is where we started to show the bicarbonate approaching the exit. It starts to break through, and then it's pushed off by the chloride, the nitrate, and the sulfate, which are higher in concentration than the bicarbonate. So it actually pushes the bicarbonate beyond its influent level. That's called dumping, where you actually exceed the influent level. If we look at what happens to nitrate, well, nitrate's more preferred than bicarb, so it takes it to a lower level. But it too will experience dumping because the sulfate is preferred. Now, if we set this up and said, what kind of safety device can we put in here? This line where the nitrate crosses the breakthrough, this represents the run length. The thing is, the sulfate being preferred continues on its merry way until the resin's totally exhausted and it asymptotically approaches the influent level. So this is what we have to design around. So you got to be careful what you wish for. We can build very selective resins. When you look at an ion exchange reaction, yeah, the nitrate and sulfate are going to come off, chloride goes in, and but those reactions are written with this symbol. That means they go in both directions. So that's great. In regeneration, all we have to do is increase the level of sodium chloride, and we can push that reaction back the other way. That's the way they're designed. But the more selective you are for sulfate and nitrate versus chloride, the more favorable that reaction goes from left to right. But the more difficult it is to go from left to right in regeneration. So the more selective the resin, the bigger the hammer that drives the wheel onto the hub, the bigger the wrench you need to pull it back off. So we look at the resin characteristics, and I'm showing a type 1, a type 2, a selective, and a super selective. Many considerations. This will help you make your choice. In a low sulfate water, the highest capacity is a type 2 anion. Then a type 1, a nitrate select, and a super select with the lowest capacity. In a high sulfate water, things change. You have the lowest capacity with type 1, a low capacity with a type 2, a little higher, and a highest with super select. Now, we take a look at selectivity because we're concerned about sulfate over nitrate. In a type 1, it's about 3-to-1. That's the chart I was showing you. Type 2, it's about 4-to-1. So it's going to prefer sulfate, and it says the capacity in a high sulfate water is going to be low. Compared to the selective, the sulfate selectivity is only about 1/2-to-1, so it's going to pick up nitrate. The super selective is 6-to-1. I mean, it's really prefers selectivity. the selectivity of sulfate over chloride. Now, this is another measure of how does this reaction actually go forward. We got very good selectivity of sulfate over chloride. That's not a good thing. Even better selectivity with a type 2. It's low with a selective and about even with a super selective. When we look at the selectivity of nitrate over chloride, and this is where I say you got to be careful what you wish for, because this is the regeneration reaction. Nitrate over chloride is preferred about 4-to-1, so it's a little tough to regenerate. A type 2 is a little easier. Nitrate select is even tougher to regenerate. Okay, and these numbers were derived from a whole series of references of benchtop experimental equilibrium studies done in the 1980s and 90s, and they're very reliable. But this is the thing. We got a 23-to-1 nitrate over chloride selectivity for the super selective. That means it may require as much as 4 times the amount of brine. So it's so selective, it's that big hammer, and you need a big wrench to pull it back off. Nitrate dumping, yeah, type 1s dump, type 2s famous for it. No dumping with select, definitely no dumping with the super select. Relative cost, if a type 1 is 1, type 2 is about 15% higher, selective is about 50% higher, and a super select is about double. Now, my choice, I go with the type 2. It's got the highest capacity in a low sulfate water. I go with the nitrate select. It's got a higher capacity in a high sulfate water. I do not favor the super select because of the difficulty in regenerating. The type 1 is usable if you have another reason to use it, such as uranium in the water that you want to pick up or some other anion. So those are my choices. And if the nitrate over nitrate sulfate select ratio, so you're going to measure the amount of nitrate, the amount of sulfate, you're going to divide the amount of nitrate by the amount of nitrate plus sulfate. If that's greater than 65%, you go with a type 2. If it's less than that, it says you got a high sulfate, go with a select. Good to know. Nitrate selective resins are actually sulfate deselective. They pick them both up and preferentially dump off the sulfate. Selectivity of type 1 and type 2 shifts. It becomes chloride selective if the TDS is above 2250. Now, remember I said you got a limit of about 2000 ppm where you can use a gel resin. The reason is that if you're up around 2500 parts per million, you're not going to pick up nitrate. You're going to pick up chloride. So nitrate selective resins are arsenic deselective. What does that mean? Well, you recall the curve, the chart where I showed the dumping. This actually occurs with a nitrate select. You have to be extremely careful. So arsenic deselectivity can lead to arsenic dumping, and let's just call it unintended consequences. You may not even know the arsenic's there. All of a sudden it shows up above the MCL. Think it through. Here's your selectivity again. Sulfate, arsenic, nitrate, chloride, bicarbonate. Here's your nitrate select, nitrate, arsenic, sulfate, chloride, bicarbonate. Why are we concerned about dumping? Well, with the type 2, we're looking for nitrate break, so the arsenic is still contained in the resin. With the nitrate select, we're looking for a nitrate break. The arsenic may have already dumped. So it depends on what you're monitoring. We're going to take the nitrate, therefore we got the sulfate and the arsenic. Here we're going to take the nitrate, we may not have the arsenic and the sulfate. Typical resin calculations. Excuse me. A typical feed water will contain calcium, magnesium, sodium, and potassium cations. The anions typically will be bicarbonate, chloride, sulfate, nitrate. I'm talking salt regenerated, so I'm not bringing silica into the equation. Now, in a typical balanced water, if you have an imbalance of cations, that means that you have an OH as a counter ion. So sodium doesn't exist in water all by itself. It either has a chloride, a bicarbonate, a sulfate, a nitrate, or a hydroxide associated with it. An unbalanced anion will have a hydrogen as its counter ion. So what are the effects of OH and H on the pH of water? Well, 500 parts per million of HCl has a pH of about 2. And being logarithmic, at 50 parts, we're about 3. 5 parts is 4. Half a part, pH of about 5. 5/100ths of a part, pH 6. If we look at the other side, 500 parts of sodium hydroxide is a pH of about 12. And likewise, 50 is 11, 5 is 10, half part is 9, 0.05 parts per million is a pH of 8. What's the pH of your water? If your pH is between 5 and 9, which it typically would be, you have no more than a half a part per million of unassociated cation or anion. So you have to be balanced. An equal number of cations and anions as calcium carbonate. Now we start with when we do a rating, we start with a balanced water analysis. So here's our cations in our typical water. And this is a high sulfate, moderate nitrate. I'm using a type 2. Here's our anions. And we have to convert our nitrate. It's given as nitrate nitrogen. So we do the math on that, and it's 53.6. So this is our, our chemical analysis for our water. When we add this up, we get 427.6. Over here, 352.9. Now this water checks in at a pH of 7. So what's wrong? Well, it was probably a $15 analysis. So what we have to do is we have to add chloride, and we add chloride because it doesn't enter into the exchange equation. It's the resin's in the chloride form. So we balance it by adding chloride, and now the two are equal. We got a pH of 7, we got an equal number of cations and anions. So we do a calculation on the type 2 by looking at the percent exchangeable anion. We're going to exchange both the sulfate and the nitrate. So we add those together and we divide it by the total, and we have 30.1%. Now 30.1% calculates out to 7.5 grams per gallon. That's the challenge that our resin will see. So we go to the type 2 chart, and we can use the type 1 on this as well. We're going to regenerate it with 10 pounds, sodium chloride, endpoint 1 to 2 ppm of nitrate nitrogen. So being a type 2 at 30%, we're going to go up to our type 2 curve. We're going to come up with 11,000 grains per cubic foot. Now, we apply an engineering factor to that calculation, and the purpose of that engineering factor, it allows for backwashing resin out of the column. It allows for a little fouling. The nitrate may creep up. What it does is it provides a cushion for down the road. You don't design the system to work on October 6th and then have it fall short of capacity by November 6th. You build that in, and it's called an engineering factor. And depending on who, what, where, and the other variables, it can be 30% or more of your total capacity. I know the state of California likes to see redundant systems, so they'll cut the capacity in half, and they'll cut the salt in half. So instead of regenerating with 10 pounds and getting 11,000 grains, they're going to regenerate with 5 pounds and say, now you're limited to 5,000 grains. So we're going to just do 85% because that should take care of 3 years of resin loss due to chlorine damage or what have you. So we have a net of 9,350 grains per cubic foot. We divide that by our calculated challenge of 7.51. It says you got 1,245 gallons as your capacity, and that's with your engineering factor. Leakage in this case is about 1 ppm. Now we're going to go to the Nitrate Select, and it's different the way we do this. We start with the balanced analysis, and we calculate the nitrate as a percent of nitrate plus sulfate. In this case, 41.7%. So our challenge is 3.13 grains per gallon. Curve looks a little different. There's 2 things involved. Since we're about 40%, we go up in between the 8 and 12 pounds to a 10-pound level. We got about 8,000 grains. So our challenge is 3.13 grains per gallon, 8,000 grains with an engineering factor is about 6,800. But again, we're not hitting it with 7 grains, it's only 3. Then we look at leakage, and we kind of interpret the leakage as being about 22.5% or 0.71 grains per gallon. The net removal is the 3.13 grain per gallon challenge minus the leakage. We're not taking the leakage out, so we're not going to count it. We're Nitrate Select. So we're only removing 2.42. So when we take our engineering allowed capacity divided by 2.42, we get 2,800 gallons versus 1,245 for the type 2. Leakage, however, is 22.5% of the original challenge level, or about 3 3/8 ppm as nitrogen. Now, if we blend these waters, with the type 2 being only about 1 ppm, we can blend 50-50 with the raw water, and we get about 2,500 gallons. With the selective resin, because we have leakage, our blend is more like a 60-40, but nonetheless about 3,900 gallons. So we can improve the capacity and lower the leakage with upflow regeneration, counterflow run, downflow service, upflow regen. We get both better capacity and reduced leakage. But just for this comparison, our selective resin in a moderate sulfate water is 58% higher capacity. Now here's a low sulfate with a moderate nitrate, and what I've done is I've kept the nitrate the same, but I dropped the sulfate level. So we add these up, we get the same kind of correction. We have to add a little chloride to get our numbers up. The total exchangeable anion now is the 20.8 plus 53 divided by 308, 24%, 4.35 grains per gallon. So we plot that out on the curve. We got about 10,000 grains capacity. With the engineering factor, drops down to 8,500, about 1,950 gallons. Again, the leakage is only about 1 ppm. We look at the Nitrate Select, and we do the same ratio. We take into account nitrate as a percent of nitrate sulfate total, 72%. So we have a challenge 3.13 grains per gallon. Plot that out. We got about a, well, it looks like 9,500 grains per gallon. 92 times the engineering factor. That's our throughput grains. We look at our leakage. Leakage is only 15%, so we're pulling out a lot more nitrate when the nitrate is a higher percent. So the net removal is 2.66 grains per gallon. Total throughput, 2940 for the selective versus 1950 for the gel. Leakage is about 2.25 ppm. When it comes to blending, with the type 2, we can still blend about 50-50. We get about 3,900 gallons. With the selective, we got lower nitrate leakage, so we can do a little higher blend. It's 55-45. We still get more capacity. However, before we had 58% advantage, now it's 37% advantage. So as the nitrate goes up as a percent of the exchangeable ions, you begin to favor the gel resin. Let's look at one more. This is a low sulfate, and I bumped the nitrate way up. So we got 3 times the nitrate with a low sulfate level. We do the addition, cations haven't changed. And whoa, what happened here? We got more anions and cations. So we add sodium to balance this out. So we either add sodium to bring the cation up or chloride to bring the anion up. So we got 406. The exchangeable anions are 44.6%. We go up to our 44% curve here. We got 14,000 grains. Apply an engineering factor. We got 11,900. That's going to give us 1,120 gallons. Remember, we got 3 times the amount of nitrate. Leakage is still less than 1 ppm. We look at the nitrate select, low sulfate, high nitrate. Again, balance. We do the calculations. We're 88.5% nitrate to nitrate sulfate. So we look at the curve. We're way up there. We got a nice capacity. It looks like about 11 and change. 11.6 with the engineering factor, 9,800. We look at the leakage. It's low because it's a high nitrate. Only 1.22. So again, we're removing a lot of nitrate. We don't have the leakage to slip by. So the throughput is 1,207 gallons versus 1,120. Leakage is 5.85. So even though we get more throughput with the nitrate select, when we blend this, we're going to see a switch. So with the type 2, we can actually do an 83-17 blend. This will yield 1,300 gallons. With the selective, we're at a 95 treated to 5 untreated water, 1,176 gallons. So now the type 2 actually produces 10% more water. Where does that crossover occur? Around 60-65%. So when your nitrate is 65% of your nitrate sulfate total, you're probably going to get more capacity with a type 2. This represents a municipal plant, and the typical installation would be 2 on, 1 off. So these could either run in parallel or probably in series. How do we design a municipal plant? About 2 gallons a minute per cubic foot, about 10 gallons a square foot. So we're maximizing the contact time and we're maximizing the flow rate per square foot. Up to a 5-foot bed depth. Life of the resin's about 10 years. Residential, we push them a little harder. We're going to beat them up a little faster. We're going to not get quite the yield out of them. We're not going to melt them as far. We may run up to 15 gallons a square foot. Up to 3-foot bed depth. The reason is at a 15 gallon a minute, your pressure drop would be pretty high, but nobody makes tanks that are big enough to handle a 5-foot bed depth in a residential setting. Lifespan 5 to 7 years. Why? This water never sees chlorine. This water does. If the nitrate is 3 times 30 ppm, 3 times the MCL, my suggestion is lead lag, 2 in series. In summary, Ion Exchange is able to reduce nitrates to less than the MCL and allows blending. There's no one size fits all. There's no one product choice that is always correct. You have to work the numbers. Type 2 resins favor lower TDS and lower sulfate levels. Selective resin is less sensitive to high TDS and sulfate and can offer more economical choice. Resin choice will depend on the level of sophistication in the plant design and the operators. If you're putting this in somebody's garage and you're never going to see it again, that's a different design than a commercial or a municipality where they monitor it every 2 hours. So the reliability factor may change your resin choice. Start with a good water analysis and a history of that analysis. You can't guess. Iron must be removed from the feed water to avoid resin fouling. That applies to both municipal and residential. Must use soft water for regeneration. I'll explain that in a sec. Short runs are not advised. I'll explain that in a sec. Acidified brine will avoid calcium carbonate and calcium sulfate fouling. Now, the short run. Okay, some of the bicarbonate is regenerated off the resin as carbonate. If you have a short run, you have more bicarbonate, you have more chance of leading to precipitation with calcium and magnesium. I was involved in a plant over in Arizona that was reporting, hey, we're getting short runs. So they shortened them and they worsened the precipitation problem and fouled the entire bed. They somehow thought by a shorter run, they didn't have to soften the water. But you can't precipitate hardness without carbonate. Calcium bicarbonate is soluble, calcium carbonate is not. The pH of your brine can run as high as 8.3. That means that some of your bicarbonate comes off as carbonate, and that's where your fouling comes from. When using a gel, you must monitor. You must have either somebody checking it in the case of a commercial, industrial, or municipal, or allow a really nice engineering factor if it's a homeowner. Your final takeaway, doing double duty with anion resin. If you have nitrates and arsenic and are using a single resin, and you opt for a nitrate selective resin to avoid nitrate dumping. Now, this is a very common path taken by dealers. Hey, I've got nitrates, I'm going to use nitrate select, and the arsenic's below the level. You will eventually experience arsenic dumping. All it takes is to run out of salt one time, and you're going to dump arsenic. Typical groundwater throughout the U.S. contains 1 ppb of arsenic. Not a lot, but when you consider dumping, it's a bunch. The West and Southwest is 3 to 5 ppb. 10% of the private wells are above 10 ppb. Just because it's not listed on your water report does not mean it's not there. All well water should be tested for nitrate, arsenic, iron, manganese, sulfate, and pH, in addition to hardness, and whatever the flavor of the day is. You may have some organic, you may have perchlorate, you may have whatever, but as a minimum, you can design a nitrate system if you know this. Why? Oh, you're treating a farmer's well for nitrate, you use a nitrate selective. What could possibly go wrong? Well, if you get iron in the water, you can foul the resin. Soluble iron can be removed with a softener, but unless planned for, it can and will foul a softener. Brine is alkaline. When you regenerate a resin, that brine, which also contains dissolved oxygen, will precipitate the iron. And but the good thing is, yeah, that will also, if you're oxidizing the iron, you will oxidize the arsenic downstream. So when you take that iron out with an oxidizing filter, you're helping yourself by converting the arsenic to arsenic 5. But iron by itself in alkaline brine will foul. Hardness. Anion resin should be regenerated with soft water. If the hardness is above 10 grains per gallon, the brine stream will precipitate calcium carbonate kicked off the anion and foul the resin, the tank, the screens, the pipe, the faucet, the shower head, all the way down the line. Absolutely guaranteed. And don't put nitrate removal resin in the same tank for the same reason. It's going to sit on top. It's going to see the water first. You want to have a softener and follow it with your nitrate system, preceded it with an iron filter. Yeah, I know, arsenic, it isn't there, but it will show up. Sulfate. The efficiency of a nitrate reduction system is highly dependent on the ratio of nitrates to sulfates, even for the nitrate selective. So take out the iron, soften the water, do your nitrate reduction, do an arsenic polisher. If you've got arsenic even below the level, make sure you've got a trap on the back end to pick that up. This way you have a happy camper. Now, if your pH is elevated, that's a red flag because you're more apt to have carbonate and you're more apt to have silica interfering with that arsenic polisher. If the pH is above 8.5, you may actually need to go find another well because it's going to be very difficult to treat without bringing that down. I'm going to throw in some words of wisdom here because I picked this up on the internet. Thomas Jefferson, 1781, once said, "The man who knows nothing and says nothing is perhaps closer to the truth than the man who spouts false facts and fantasies and blows smoke out of his yin-yang." Well, I paraphrased that a little bit, but the point is that if you don't know what you're talking about, it might be best to not talk. Now, President Reinecke once said, "A half-cocked gun cannot be fired. A half-cocked salesman should be."
Amen.
And I add my 2 bits to this, saying, ignorance is not the enemy of knowledge. The enemy of knowledge is the illusion of knowledge. You got to know what you don't know. Don't pretend you have the answer unless you do. These are the references that I use to pull this together. If you get a screenshot of that, I think you will enjoy reading up on this because the whole history that I've kind of broken down into a thumbnail sketch is contained in these articles. So thank you very much for your attendance. Any questions, somehow get them to me. Become certified, become part of the solution. So this is me. That's it. I thank you very much.
Wow, Chubb, thank you so much. I mean, the amount of knowledge right there that you've so generously donated is just incredible. So thank you again for doing that. So some key takeaways that I immediately heard that I think we need to reiterate to everyone is calculate your sulfate nitrate ratios. Remember, in the West, arsenic's going to be there whether you think it's there or not. And then fools rush in where angels fear to tread. Consider the consequences of failure. I mean, 30 years ago, when you and I were talking about commercial design, you always told me there's no difference between commercial and residential when it comes, or industrial, based on the size of the equipment. You said it was all about consequences of failure, and I've adopted that to heart.
It's a good philosophy.
What do you think of the consequences of failure here? Let's scare everybody a little bit more and make sure that they don't go running off and treating things that they perhaps need to learn more about before they dive into it.
Well, the best advice is that, when you're dealing with a softener, Sure, you can shut a boiler down, but as far as residential, you're going to get an angry housewife that says, hey, my dishes are spotted. And the little girl in the family is going to say, oh, my hair's all gummy because the water's so hard and it reacts with the soap. But nobody's going to die. When you're dealing with an anion, it's like having a series of prescription drugs in a drawer and you reach in and grab one at random. That's not a good way to do things. You got to know what you're doing. And as I pointed out, the enemy of knowledge is not ignorance, but you got to realize if you have ignorance, you got to ask somebody. Plenty of people around that know what they're doing, and you got to have a good analysis, and you should have somebody looking over your shoulder. The unintended consequences, if everything's running right, maybe nothing happens, nothing wrong happens. But as soon as something goes wrong, what's going to happen is not in proportion to what went wrong. It's going to be tremendous. So make sure you know what you're doing. That's the main takeaway.
Oh, that's excellent. Thank you. So fools rush in where angels fear to tread. Don't even dare treat nitrates unless you actually have a good understanding, and make sure your vendor, your supplier is backing you up. Ordering stuff on the internet out of a catalog, and if just because it says it's a nitrate filter doesn't mean it's the right nitrate filter for you. And so every application is tailor-made.
I would add one more little piece of advice, and that is that although a gel resin may be less expensive, and even though it may give higher throughput, if you run out of salt, it's going to dump. Taking a nitrate selective approach, you're protecting against that. You just have to back that up and make sure you're not dealing with arsenic or something else that might slip through. So the safe bet is it's hard to go wrong with nitrate select. But again, if I don't have a really high level of confidence in the water analysis, I might apply a 50% engineering factor.
That makes a lot of sense. Chubb, thank you again. I truly appreciate your time that you give so generously to our industry. I think Chubb would agree with the shameless plug I'm going to give now for WQA's modular education program, since he helped to write a lot of it. Get certified. And now more than ever, it's a great time to be in the water business, and it's the appropriate time to get your education, get your certification, get your credentials so that you can do it right.
Very good, sir. Thank you much.
Thank you, Chubb.